Okay, Lagrange equation. Now, I forgot in the last video to say two upsides with the Lagrange equation. Now, the first is that it has the same form in any coordinate system. It means that if I have some force, that was a stupid vector, but I have some force on a particle. Do it like this instead. If I have some force on a particle, that force, right, that force in the x direction is just mx double dot, right? If I write it in terms of y, it will be the same. But let's say I now modeled the same position, nothing's changed, but I model it in polar coordinates. Now, the phi equation or the r equation, I don't remember, will be different. What it means is that we now have representing the same thing, but our equation is different. We don't have the exact same form. Of course, it's the same position, but the equation doesn't have the same form. But if I did the Lagrangian, look here, if I did the Lagrangian now, the Lagrangian will just be d over dt and partial Lagrangian in terms of x dot. And this will be the same. I just substitute x here with phi. I can substitute with r, whatever. It will always be the same. Okay, so that's one of the main advantages. And the second one, I said it not entire precisely last time, but if I had some path like this is a wire, not path, but it's a path. But let's say I had a wire and I have a bead on the wire, like I said. I stated last time that the thing is that the normal forces are very cumbersome to calculate. I should have stated that we don't need to find the normal forces. I said that somewhat, but you don't need to find the normal forces, and they are pretty hard to find. When we have this constraints problem, the Lagrangian totally eliminates the normal forces because we only care about the start and end. And when we model the particle, we only care about the optimal path. And the optimal path is in terms of energy, so we don't need to calculate the normal forces. And they are pretty hard to calculate. So I should have stated that the Lagrangian just eliminates the normal forces because they are pretty hard to find. Okay, perfect. Now we can move to the Lagrange equations themselves. So let's now think, okay, we have some particle. And that particle is in 3 dimensions, and it's subjected to some force, and that force is a conservative force. Now this conservative force here, of course, we can write it in terms of energy. So the first is the kinetic energy. The kinetic energy is written in Lagrangian as T. I think it has something to do with French, but I'm not quite certain. But this T instead of Ke is just M times V. I could just to make it a little bit clear. We have 3 dimensions, a particle, some velocity, and of course subjected to some force as well. Okay. Okay, and that particle, let's see, and then we can write this as 1/2 m. We have r dot squared by r, because of course we want the parametric form. We don't just think in x, y, and z, because of course a particle can spiral like this. This will defy what it means to be a function. So in the parametric form, and then we just use r dot notation because we have time. And this can of course be written as 1/2 m x dot squared plus y dot squared plus z dot squared. Now you may ask, why not this guy squared? Now the reason being is that in every type problem I've done, it's the same. When we model in terms of components, the vectors, if it's spherical or Cartesian or whatever we model in, we always end up having the unit vectors or the components perpendicular. When we have them perpendicular, if you had something like, let's say you had let's say you have this for some components, so you have a squared, then you, of course, you'd have 2ab. If I had a plus b here, 2ab and b squared. Now b and a, since they are components that are perpendicular, if I had a hat, and I multiply that by b hat, you can just have 2 in front of there. They will, of course, cancel and will equal to 0, right? Because they are perpendicular, of course. So that's why we get just x squared, y squared, z squared, and not the whole parentheses squared. Okay. Then we have just the potential. It's just the potential in terms of position. You can, of course, have spring potential here, but I guess you could also have from electromagnetism, but you, of course, use the gravitational potential in this case. That's what we usually will have. So I just have x, y, and z, just in terms of position. Okay. Let's see now. Okay, it could actually be a spring in this case too, but it's just some potential. That's it. Okay. So now, if I have the Lagrangian, as stated, was defined as t minus u. So if I now do partial Lagrangian in terms of x, d over dt, and then partial Lagrangian in terms of x dot, right? If I do that, you could see that partial Lagrangian in terms of x, that will just be from the position. So that's just a force, because if I have, I could just write it so it makes more sense, but it is minus partial u in terms of x, and then I get d over dt. I had mx squared 1/2, the 2 goes down, so it would just be mx dot, like that. And this guy is just the force in the x direction, because so if we have, of course, a derivative, or if you have, of course, the gradient of the potential, now we just have partial, but you have gradient potential is, of course, a force. And then d over dt of m and x is, of course, a function of time, so we just have x double dot. And now we arrived at a very interesting conclusion. So with the Lagrangian, t minus u here, with the Lagrangian function, we arrived at Newton's second law. And we know that Newton's second law predicts the path, in this case, of the particle. But the Lagrangian equation arrived at the same conclusion, i.e., they are the same. There are 2 different models, but still representing the same phenomena. So you can represent nature in different ways and still arrive at the same conclusion. Very neat. And also, what is pretty interesting here is that you can see that this equation right here, as we have here, this equation right here is the same equation that we had from calculus of variations, which means that the action integral S is equal to T1, T2, and we got the same equation if we did the partial of the Lagrangian like we did the partial of the function from the calculus of variation, which means that the function is the Lagrangian, and now we have dt. This means the third statement here. We have the first statement, Newton's second law, that we, of course, always knew, but the second statement was that the Lagrange equation arrived at the same conclusion. Now the third statement is Hamilton's principle, which is that since this L here did the same thing as if we had the function we had yesterday, not yesterday, but in the last video, since we arrives at the same Euler-Lagrange equation with the Lagrange equation, it states that this action integral, when it's stationary, that is the actual path of the particle. And we know that because the optimal path was defined when, in the last video, when we had a function here I had in terms of x, but I stated that you can, of course, use t as well. So in the last video, I stated that this integral right here, its optimal path is when this was stationary. It was the same thing as finding when the derivative was stationary in terms of a point, but this is now in terms of a path, right? Because we have collected all the small pieces and now we have a line. And of course, the optimal line or the optimal path is when this action integral is stationary, i.e. the principle of least action. And Hamilton's principle is that now we could see that the Lagrangian equation had the exact same form as we did with the calculus of variation, which means that that is also true for the Lagrangian equation. So you have three statements representing the same phenomena in nature. Three different models arriving at the same conclusion, which is pretty cool. Okay. So now we have that, of course. From here, we can see that it's pretty simple as well. I could have written anything here. I could have written a coordinate like phi. I could have written a coordinate like theta. We could have spherical coordinates. We don't need Cartesian, because now the statement we had was that in terms of Newton's second law, Hamilton, and of course the Lagrangian, we looked at the Lagrangian and Hamilton in terms of Cartesian. But this is also true if we have, of course, polar coordinates or spherical coordinates, right? And cylindrical coordinate, it still would be true. So those statements are not just equivalent in Cartesian, they are equivalent anywhere. And that makes sense because position don't care about if you model the position in Cartesian or model in polar, it doesn't care. It's still the position, right? Okay, cool, right. Okay, the next thing here is that when we do, right, this guy, when you do the derivative here, this will be a force, right, usually. But we call it the generalized force, and we call this the generalized momentum. And the reason being is that we're not always going to have a force. We may have a force in terms of an angle, i.e. a torque. We may have a momentum in terms of an angle, i.e. angular momentum. And you will see that it will make much more sense with an example. But that's just some notation that's nice to have. Okay, so let's move on. We saw that this worked in Cartesian, so I'm not going to do the two-dimensional case in Cartesian, so we can just jump straight to the polar coordinate example. So let's say you had, oh no, not like that, I'm a moron. Let's say you had a two-dimensional case. You had a particle right here. It's r up there. This is a component r, not a vector r in that case. It's a component up there. And then you have the position of the particle determined by polar coordinates. So you have just r and the angle phi, because we're doing physics. And then we want to, of course, determine its equation of motion, right? In order to do that pretty simply, instead of doing a lot of calculations, I love arriving at the problem with using the least amount of energy. So I'm lazy as well, but you could just say dr here. So if the particle moved some dr, so we have dr vector here, it has to go in the phi direction. And this is phi in the phi hat direction, so d phi. But you can't just move an angle. That makes no sense, right? If I had, let's say I had angle here, this is not the same as moving this distance here, but we're moving the same angle. So of course I have to compensate. And what do I have to compensate by? I have to compensate by r. Pretty easy to think like that. And of course, the other component is r. So this is dr in the r direction. Don't be confused by this guy with this guy. dr is the total movement of the particle. And dr in the r hat is in the r component-wise direction, right? That we moved. Okay. Okay, then I can pretty simply write dr vector is just dr r hat plus, of course I need r times d phi and then phi hat. Now I can just divide by dt, then I get r dot is equal to r dot in the r hat direction plus r d phi, which is just phi dot in the phi hat direction. Pretty easy. Okay. We need r dot because we of course need that for the kinetic energy. So the Lagrangian in our case is t minus u. That will be 1/2 m. And now r is r dot squared plus r squared and of course phi dot squared like that, minus the position, and position is in terms of r and phi. Okay, now we have two coordinates. So we have two coordinates here. I of course have to do them separately. So I have the r equation. The r equation will be partial Lagrangian in terms of r, right? That's equal to d over dt. And that's partial Lagrangian in terms of r dot. Now, partial Lagrangian in terms of r, that gives us two terms. It gives us, because we have, I can write it so I don't have to be a moron. Partial u in terms of r, but we also have plus, we have r squared phi squared. So r squared, I just get m r phi dot squared. So just m r phi dot squared, and that's equal to d over dt. And that's just d over dt and just m r dot like that. That's perfect. Okay. And if I write this guy, remember derivative in terms of the potential, that's of course just the force in the r direction. You can move this term on the left. You can move this on the left side, right? And then I get just m. I can just do m as a common factor. I get r double dot and I get minus, and then I have r phi dot squared. And this makes sense because this is the force in the r direction and this is the non-centripetal acceleration. So what we modeled is the force here, right? So this makes sense for now, and the only thing missing is now, since we're thinking in terms of polar coordinates, we need some kind of force that goes like that. That would make sense. Thinking polar coordinate, we need something like, you know, pushing on a door, i.e. a torque. So let's see. Okay. So for the phi equation, the phi equation would be partial Lagrangian in terms of phi is equal to d over dt. Then we have partial Lagrangian in terms of phi dot. Now partial Lagrange in terms of phi is minus u over partial phi, and that's equal to d over dt. d over dt, and that one is a little bit special because we have still r squared there, so it'll just be m r squared phi dot like that. Now to interpret this guy, we need to do something. There are some clues here. First, this guy right here, this is the angular momentum. That's, like I said, why this is called the generalized force and generalized momentum, because in the first equation, this guy is the actual momentum, right? This is the momentum in the r direction, while this guy is actually the angular momentum right here. Okay? And in order to interpret the left side here, there are already some clues, but in order to interpret it, we need to write the gradient of the potential, because the gradient of the potential is by definition forces. So if you do the gradient of the potential, we'll get partial, and again, nabla is a vector quantity, so nabla times a scalar u, which is the potential, will give us a vector quantity. So it's partial u, partial r, and since it's a vector, we have r hat, plus partial u and partial phi. But again, this is not a force, but it has to be a force. So to compensate again, because it's an angle, we need 1 over r. This calculation is a bit tedious to derive, so we're not going to do that, but to understand this pretty easily, because now we can use this guy, because I could state that the force, because by definition this is the force, so the force, I could say it like this, so the partial u minus partial u of phi is the force in the phi direction, or it's not the force, my mistake. It's not the force in the phi direction, but this whole quantity here is the force, which means that we have the force in the phi direction is equal to minus 1 over r partial u and partial phi. And if you move r over there, what happens then? You have, of course, r multiplied by f of phi, which is an torque, right? Exactly as we expected. Because now look what I have. I have on the left side here, I have r multiplied by the force here, which is equal to mr squared and phi dot, and we have, of course, phi double dot here. And to make this even more neat, what we have on the left side is the torque, right? And we have d over dt of the angular momentum. So what I have is that the torque is equal to d capital L over dt, like that. And now we're finished, because this makes sense now. If you look at our graph here, we have the forces that aligns with r in the r direction and centripetal acceleration. And what we're missing was some force alongside the circular motion, right? Because then we could, of course, determine the path of the particle in this polar coordinate system, right? And what we were missing then, of course, if you have a force that goes like this, it's not just a force, it's a torque, of course. And that is exactly what we got. Pretty neatly. Okay, that is enough for me. In the next video, I will, and the last video for this summer, I will do some problems. You can, of course, go more in depth in terms of there's proof on the constraints. You could also do the Lagrangian with t at the end. So now when we did the Lagrangian, if you had some, if you have for the generalized coordinates, so that, let's say I had q1 here, and I have q1 dot, I could also have t. And t is very useful if you have some coordinate system, and that, let's say that particle or whatever that object is, without time, you may end up being in an accelerated system, i.e. a non-inertial reference frame. And you can use time in order to get out of that. For example, if you had, let's say you had a car here, and you had a pendulum like that hanging from the car. Now when that car accelerates, the pendulum doesn't know what the acceleration is. And in order to get out of that, so you don't have that non-inert, so you don't have that accelerated reference frame, you use time. That's just. You also have some words on holonomic systems and, of course, degrees of freedom. But again, this is enough for me. I'm satisfied with that.